Okay, let me share my screen. Can you see my screen now?
Yes.
All right. So today I'll continue the tutorial 1. Yeah, we are going to finish it today. Here. So let's review the problem. So this is a circuit for biomechanical electronics. So in this circuit, first we pre-charge capacitor with the initial voltage VH. Okay, and so at the beginning the switch is off, so there's no current at any branch, and then switch start to turn on and we start to record the time. Then the capacitor start to discharge. Okay, discharge go through the branch of inductor. So here the question is to ask you to calculate some parameter for equation 1 up to 4. So the first one, you are asked to find the time response of the coil current after the switch is closed. So after this one is closed, then the current flow through the inductor L, and so you need to find the equation, the governing equation for the current IL. So the function is in function of initial voltage VH. So here you see the notation VC. VC is instantaneous voltage. VH is the initial voltage, which means VC at time 0 equal to VH. Okay. So last week, 2 weeks ago, you have already derived the equation for the to describe this circuit when S is closed, right? So again, let me explain what happened when S is closed. So S is on, the capacitor discharge, and diode is off. So you only have the circuit with current flowing this way. So the current start to increase from 0 to certain value due to the spinning inertia of magnetic flux. Yeah, because the current push the magnetic flux to spin here, so it increases little by little. When the VC is 0 and part of the current from inductor continue to flow to charge the capacitor with reverse polarity. Actually here we cannot say it 100% because it depends on the value of parameter R, capacitance and inductance. So just suppose it might happen if resistor is large, then the inertia of the energy stored in the inductor continue to suck current this way. But if resistor is too big, it may also charge capacitor in the reverse polarity, but it's not always true. Just make assumption first. And the other part of current flow through resistor, which automatically turns on D. Yeah, for this one is for sure the current continue to suck by inductor and push this way. Okay. if resistor is very small, then current can only flow this way. No more, there's no charge on capacitor in the reverse polarity. We will verify that, and I will show how to verify that. So when S is on at time 0, so T taken from 0 to a certain value T1, then the instantaneous voltage on the capacitor start to decrease, right? Decrease from the initial value VH until 0. So in this period, S is on and D is off. Okay, so from this circuit you can derive the equation. Okay, equation of the circuit with two components only, capacitor and inductor. So the equation has this form, second order, and with initial condition voltage at capacitor is 0, and initial current, which is proportional to derivative of VC, is also 0. So you solve this equation to find VC. Okay, I'm not going to show the detail how you can solve, because this is just second order ordinary differential equation. So the solution for VC is VH cosine T over square root of LC, and then to find the current, because current go through capacitor and current going through inductor are just the same. Sorry. Okay, so feel free to interrupt if you don't understand. So I can be found by just taking the time derivative of VC. Yeah, actually when you write IC, when you use the formulation IC equal to C dVC over dt, you suppose capacitor as elements, not source. It means IC going this way, you assume this way. But in this case, capacitor discharge, the current flow this way, which is minus IC, like this. So actually IL is the same as minus IC. Okay, IL is same as minus IC. So back to the question number. Well, I need to confirm that this is the solution of question number 1. Okay, the answer of question number 1. Oops. Time response of the coil current. Okay. Now question number 2. Peak coil current. Peak mean the maximum current. If the initial voltage of capacitor is 950 volts. Okay, so so IL is minus IC here, and you see that this is a sine function, and minus of this you have plus here. So if you draw the sine function, you get something like this, start from 0. Okay, so the maximum is here. Okay, maximum, so the peak time T1, right here, T1 that I show here, T1 is the time where current IL is at maximum value, which means sine of T over square root of LC equal to 1. Okay, so at this point IL max equal to square root of C over L VH sine equal to 1. Okay, maximum. Is there any question? Bunsro, is it okay?
Sure, I think internet here is not okay. Like I didn't see their slide. Like the slide is, I didn't see the graph. Like you're talking about the graph, but I didn't see the graph. Maybe my internet is not
Really?
good. Yes.
How about other Vatana?
I can see it, teacher.
Oh, so it's problem with your internet connection, Bunsro. Anyway, I record the all my lecture and I will upload to the website. You can watch it again. So is it okay, Vandana?
Yes, teacher, it's okay.
Alright, then question number 3. I guess the compulsory is peak time, right? Yes, the time T1 at which diode turn on. So how diode is turned on? Yeah, when the capacitor voltage drop to 0, there's no potential pushing from the upper part, right? No more. So the energy stored in the inductor continue to the current continue to flow, but in the form of discharging energy. Okay, discharging the energy from inductor, so it goes through the diode branch, right? Because resistance is small, actually very small, 85 milliohm. So the moment VC is 0, D is on. So VC is 0 means cosine is 0, which is the same as sine is 1. So actually T1 here at the peak time is the time that diode turn on. Okay, so T1 equal to D, I would say D start to turn on at T1, and T1 equal to actually T1 over square root of LC equal to 90 degree, which is pi over 2, because sine equal to 1. So you can have T1 equal to pi over 2 times square root of LC. Okay. Then question number 3. This one T1 equal to this. And then question number 4. The energy dissipated in the resistor for VH equal to this. Okay. Initial capacitor voltage is 950 volts. So the number 4 is to ask you to calculate the energy dissipated in the resistor. So let me ask any idea from you how you can calculate energy dissipated from resistor. So first let me ask Lisa May, can you give any idea or just formulation? How do you find energy dissipated in the resistor? Lisa May?
Yes, teacher.
Can you give any one idea? Did you say something?
No, not yet, teacher.
How about Sayla? You have any idea how to calculate energy dissipated in the resistor?
Sure, so that we have to know the current, the voltage, and the time passing through the resistance at 85 micro.
Okay. And can you give the formulation to calculate the energy dissipated here?
And so that Q equal to V IT.
What is it?
Q equal to V IT. Is it correct? Teacher?
V is time
I'm
I
not sure.
and
And T.
T.
Time. Yeah.
Well,
Q is
this you can use this formulation. So let's say VR, IR, and time. Well, this formulation is for static circuit. I mean for constant current, constant voltage, right?
the teacher.
And let's call W. Well, actually you start from the power equal to V times I. That is okay, but then energy is integral from 0 to T, so it depends on how long you want to calculate the energy dissipated from the resistor. So it's like this. Okay.
Yes, teacher.
Yeah, it's close actually, because current IR is not constant, VR is not constant either. Okay. Yeah, so to think from the bottom up, yeah, because you can see here, if you notice, I use approach 1. Difficult. Approach 1 is to think from the bottom up, which means, well, you see the question energy dissipated in the resistor, then you start from the resistor itself. So this is the formulation. But in order to find this integral, you need to know what exactly VR and IR. So yeah. Okay, so first let's think about the period of what happened when the energy discharged from inductor going through diode. So T is taken from T1 to infinity. Let's say dissipated, the energy dissipated in resistance, it's dissipated little by little, so energy will be totally released when T goes to infinity, right? Okay, because we don't know when exactly all the energy will be dissipated, right? So in this case, S is on, D is on. So you have the full branch circuit, including capacitor, resistor, and inductor. So you derive the equation, the governing equation for the circuit. You start from here, VC as a source, and here branch VL and VR. So, and you use formulation relationship between current and voltage for capacitor, and then current and voltage for inductor. So finally you can derive second order differential equation like this. Okay, yeah, if you still remember, you have 1L and resistor with parallel with capacitor. Equation always has this form, 1 over RC, 1 over LC is like this. And for this equation you have initial condition for the current on the inductor. The initial is at T1, right? So IL at T1 equal to I peak that we calculated in the question number 2. And the time derivative of current at inductor at time T1 is 0. Why is 0? Because here you see the slope here. Slope here is 0. Okay. Then you can solve for IL from here. Once you solve for IL, you can find IR. Here is IR, just minus L over R time derivative of IL. Okay, so you got IR here. How about VR? Well, VR is just IR time R. Okay, so you got IR here, and VR just IR time R. Then you can substitute into this equation and integrate this term. Okay, and T, well, T here because the amount of energy, we need to calculate the amount of energy dissipated. Then actually T here is approach to infinity. Okay, T approach to infinity. Yeah, this is the bottom-up approach. It seems a little bit difficult because you need to follow several steps, as you can see here. And so now let me ask, anyone can have another idea which is which could be easier. Mode, did you have any idea? Okay, so let's okay, so we can consider about energy conservation. The energy that had been stored in the inductor, right, will be released and dissipated via resistor, right? Energy stored here will be dissipated via resistor. So actually you can say, well, energy dissipated here can be calculated by just integral from 0 to infinity throw to T1, because you have, let me write down again, you already have VL and IL right? From the what you have found here, or not IL and VL, but IC and VC instead. Yeah, but IL is just minus IC. Okay, so you have IL, and VL is just L DIL over dt. Well, then yeah, you have IL here, which is, let me write down, square root of C over L times sine of VH sine T over square root of LC. Okay, so you have IL, and VL can be found by taking time derivative of this IL. Then you calculate the energy stored in here, because IL here taken from 0 to T1, right? IL VL. Okay, this is approach number 2, which is easier because you don't need to calculate IL when the time taken from T1 until infinity. This IL is IL discharge. This IL is IL charging, store energy on the inductor. Okay. Well, you can also say that, oh, this is just the same as IC. The energy stored in inductor is just the same as energy discharge from capacitor. So which means you can integrate this the product of VC and IC. Okay, but same thing for here, exactly same thing. And yeah, so in some sense this is not very bottom up approach, because you think not directly starting from R itself, but from the inductor, which transfer energy to R to be dissipated. Another approach, the third one, which is the easiest one. So anyone has an idea of that approach? Watana and Udam, both of you have any other idea? That one is very bottom up, very top down approach. Things, you think using your right brain. If the bottom up approach, you think your left brain, So try to see things in big picture. Then you use your left or your right brain. Hold on, you want to say something? And Vatana, you say something? I heard something, but then disconnected. Vatana?
I don't have any evidence.
Sela again.
I didn't hear it.
Udam?
I really don't have any idea.
Sinh Hui, how Sinh Hui? try to
I
see
don't have any idea, teacher.
try to see things in big picture, so it will make your life easier actually. Well, the third approach, okay, so the energy that you have at the beginning is the energy that you store in the capacitor, right? So this energy is going to be transfer from capacitor to inductor, and then inductor to resistor, and then dissipate it. But so in the beginning, the energy is just energy of capacitor, and you know the formulation of energy in capacitor. Well, so here is the integral of the second approach actually, but finally you just get the formulation energy is just 1/2 C times VH square, and this is just energy that you pre-store in the capacitor, right? So actually you can immediately write down, well, the energy dissipated in the resistor is just energy pre-stored in the capacitor, which is 1/2 C VH square, and the minus sign that you obtain from calculation here actually just to represent the discharge, okay, because we calculate it using the formulation during the discharge here. Sela, you remember this formulation?
Yes, teacher.
Yeah, so see, try to thinking something in big picture. Sometimes it's very easy. Is there any question in any detail of process or calculation?
Teacher, so to sum up with this case, if we want to find the immediate energy, the energy that is dissipated, we have 3 approaches to find it.
Yes. So I'm trying to show all this approach to stimulate your thinking, or to show the possibility or the way we can think about it. Usually, engineer think from the bottom up. I mean, think from the logic very, very bottom up, like the first approach. Okay. Usually, but if you train your brain on the right side to think something, to try to see things in big picture, you can come up with a simpler approach. Okay.
Yes, teacher.
Any other question? No more question.
Teacher, I have a question.
Okay.
Teacher, with this 3 approach, we can use our cases. I mean,
What?
like for this exercise, we can use one of them to find it. How about other exercise?
Well, yeah, the main idea is to see the sequence energy. You need to track all energy, okay, energy stored in somewhere and then discharge to somewhere, because this problem you don't have dissipation during the discharge from capacitor, right? So you can conclude that all the energy discharged from capacitor will store in the inductor. Let's say if you have another resistor in here, which is usually the case, because it can have very small internal resistance. Let's say you have resistance here also. Then the energy that discharged from capacitor also dissipate via another resistor here. Let's call R1, at the same time it's stored in the inductor. Okay, so in this case you cannot say the energy stored in here is same as here, right? Because you already dissipated the energy, some part of energy dissipated here. So this one is not so easy to think using the top-down approach. Okay. But anyway, you may think, well, you can find the current through here. You know the energy dissipated in here, and the remaining will be stored in here. And after then, the remaining that stored here will be dissipated through here. So in that way, in some sense, still easier than the bottom-up approach, right? The brute force approach. We can say brute force approach. Brute force approach is hard. So still, you still using this thinking. Do you understand, Sela, what I mean? Because this is a little bit abstract.
Yeah, that's it.
Okay. Any more question? Sinh Hui, are you okay?
Yes, teacher.
All right then. So before I continue to the next lecture, let's take a break about 5 minutes. So we're gonna restart at 2 past 10.